Okay, so the next homework assignment is not due until the 24th of September, so you've got a little bit of time to work on that. I'll upload that assignment to MU Online today so you can get started on it. It's covering some of the topics that we're going to delve into today, including atmospheric pressure variation, manometers, and then some of the first applications of the hydrostatic equation. Any questions related to the announcements? All right. Do you remember the piezometer I talked about at the end of class on Tuesday? The piezometer. It would be that inconvenient and impractical way of measuring pressure in a water pipe. What are the reasons why a piezometer isn't a very good way to measure water pressure? Yeah.
Well, to dig up the hole, you need a log to be the height change.
That's right. So the delta H would be very tall for the typical pressures that we see in a pipe network. And then the other issue is that a piezometer is open to the atmosphere. And so dust, contamination, birds flying over it, it just isn't a safe way for potable water that's supposed to be clean. A U-tube manometer is a way of getting around some of those limitations. The other issue with the open piezometer is it's not usable for gases. Remember, it could only be used for a liquid. A U-tube manometer, the idea here is that we're using two different liquids. There's whatever liquid is flowing through the pipe, but then we're measuring the pressure difference using what's called a manometer liquid. And so the idea there is that generally you'd want to utilize a fluid that has a relatively high density. And the more dense the fluid, then that deflection distance, delta H, doesn't have to be as big as like the 85 meters that you'd have to have if your fluid for measuring pressure differences was water. All right. So in a problem like this, they're often set up where they're asking you what is the pressure in the pipe based on some dimensions that are measured. And so in the middle of the pipe, here at location 4, is where you'd be trying to calculate the pressure. And you start where you know the pressure. And you can notice that this manometer is open to the atmosphere. That extra distance on the side is kind of implying that we have a free surface of the manometer liquid that's vented to the atmosphere. And so the pressure at 1, where the manometer liquid is in contact with the atmosphere, before we've gone down through the liquid at all, just right here at the surface, the pressure is 0 gauge. And so we're just going to do a counting from there. Anytime we're going down through the fluid, the pressure is increasing. Anytime we're going upward through a fluid, pressure is decreasing. So here, our calculation strategy is pressure at 1 is 0. Pressure at 2 is pressure at 1 plus some change. And we're going to use the hydrostatic equation. Delta P is delta H times gamma of whatever fluid we're going through. So here in this first illustration, let's say, for instance, that we have water that is at 10 degrees Celsius is what's flowing through the pipe. And then the manometer fluid that we're using is mercury. And mercury is a good manometer fluid from the standpoint of it's very dense. And so you won't have to have a large delta H to measure pretty large pressure inside of the pipe. So mercury is useful in that respect. It's also not so good because it's toxic. So you wouldn't want to have it in contact with drinking water. But this is just, the fluid mechanics fundamentals here we're talking about. So we'll set aside toxicity for now. Let's find the pressure at the center of the pipe. Okay, so the way that we do that is, first of all, P1 is 0. It's in contact with the atmosphere. P2 is P1 plus delta P. And it's plus because we're going down through the fluid from 1 to 2. And pressure accumulates positively as you go down through the fluid. So to expand that, it's going to be 0 pressure at 1 plus delta H times gamma M, where gamma M means the manometer fluid. Now, off to the side here, we should define that our unit weight of water, let's use a unit weight of water, 9810 newtons per meter cubed. And then for mercury, it's going to be 13.6 times 9810 newtons per meter cubed. So our manometer fluid has a unit weight of 133.416 newtons per meter cubed. Okay, so the pressure at 2 will be the distance. So it says in the problem statement it's 45 centimeters that we're going down through that delta H. So 0.45 meters of mercury. So multiplying the 0.45 by 133.416 newtons per meter cubed. And that tells us the pressure at 2 is 60,037 pascals. So that's the pressure at 2. Now think about what's happening inside the manometer as we go from 2 to 3. So as we go down through the fluid, the pressure is increasing. Going sideways doesn't have any effect on the pressure. But then as we're going back up through the fluid, the pressure decreases again at the same rate that it was previously increasing. The point is that the pressure at 3 and the pressure at 2 are the same because they're at the same elevation, and we went through just a single continuous fluid to connect them. So the pressure 2 and 3 are equal. So I'm going to say P3 equals P2 equals 60,037 pascals. So that's the pressure at 3. And now the pressure at 4 is P3. Now is it going to be plus or minus the delta P?
Minus?
It will be minus, that's right. So minus the delta P between 3 and 4. So the other way to express that is minus delta H, which here, instead of delta H, the variable for our height parameter is L. So I'm going to say minus L, that distance that we're traveling upward through the fluid. And now we have to use the unit weight of whatever that fluid is. In this case, it's the water. It's not the mercury. So L times the gamma of water. Okay, so P4 is going to be 60,037 pascals minus 1.83 meters of water, 9810 newtons per meter cubed. And this change in pressure, it's going to be a decrease of 17,952.3 pascals. So in the end, our overall pressure at 4, let me just bring the solution up on the screen for the benefit of anyone who may go back through this later. All right, here it is. .1 kilopascals. So the pressure at the center of the pipe, even though the water is flowing through the pipe, conditions are static inside of the manometer tube. And so we can apply the hydrostatic equation. And you know, there's this section that we went through the pipe where it wasn't static conditions. You know, water is flowing through the pipe. But as long as we aren't going side to side, there won't be much of a pressure difference between the center of the pipe because the water is flowing versus if the water was static. So in other words, if we go from the opening of this manometer up to the center of the pipe, it's still okay to apply the hydrostatic equation. Any questions about this first example? All right, we can apply it in situations where things are more complicated, like this kind of a manometer, which has 3 different fluids. It's got a water pipe and a static tube that's connected to the water pipe that's filled with water, and then oil, and you notice the specific gravity of the oil is specified, so we can get a unit weight from that. We're going down through the oil, and now we're in mercury. Again, we have the specific gravity defined for the mercury, and then finally another segment of water. And so in a problem like this, the unknown is at A, and where do we know the pressure? At 1, that's right. He's right. Why do we know the pressure at 1? Because it's open to the atmosphere, and we know that the pressure at 1 is 0 gauge. It's just the same pressure as the air that surrounds this entire system. Okay, so if you want to find the pressure here at A, the way to solve it is the same as in the previous example. You start where you know something and work towards the unknown. So we can say P1 is 0, P2 is P1 plus the delta P between them. So you would use the hydrostatic equation, you'd have some distance parameter, you'd have the unit weight for water, and you'd calculate P2. So I'd like you to do that. I'd like you to go through the steps and calculate the pressure at A. Now I'll point out something that is important, and that is that the pressure here at 2, that's not the same as the pressure in the oil over here. You can only say that the pressure is the same at the same elevation if they're continuously connected by a fluid. So pay close attention to what is the elevation difference between the 2 points. So for instance, it's 90 centimeters from 1 to 2, 30 centimeters, and another 30 centimeters from 2 to 3, upward from 3 to 4, 150 plus 30, and then just 150 down from 4 to A. All right, so I'm going to stop talking, give you a chance to collaborate with your classmates here. You're going to have to calculate the unit weight for the oil and for mercury, but then beyond that it's just plus when you're going down through the fluid, minus pressure when you're going up through the fluid. All right, so we've got 3 different fluids with 3 different unit weights, the water, the oil, and mercury. So we need to kind of have that information available when it comes around. The pressure at 1 is 0, and then we're going down through the fluid, and so the pressure increases, and at 2 it'll be 8,829 Pascal. Then at 3 it increases a little bit more because our net elevation decrease, so we're going down through the fluid. The 0.6 meters of mercury is going to add now 80,000 pascals. So that means that the pressure at 3 should be a total of 88,878 and 0.6 of a pascal. Now as we go from 3 to 4, the elevation difference is 1.8 meters. And you know the dimensioning is a little tricky there, right? 150 centimeters, but then also that 30 centimeters. Okay, so back here to the solution. The pressure at 3, we calculated the pressure at 4 is going to be whatever it was at 3 minus, because it's an elevation, you know, we're going up through the fluid, so the pressure is lower. And this time it's through oil, so we have to use the oil unit weight. And then finally, the pressure at A will be an additional 1.5 meters of water. which gets us 14,715 pascals, and so 89.5 kilopascals is what we should get in the very end. Any questions about this manometer? So think about the types of problems that could be constructed with a manometer like this. It could be that the pressures are given and you're asked to calculate the unit weight of the fluid or the specific gravity or the delta H. It's just any one of these three parameters in the hydrostatic equation could be the unknown that you're solving for with a diagram of dimensions and pressures and different fluids. Just apply the hydrostatic equation. Any questions? All right. So a manometer that's open to the atmosphere is what we just saw. Another type of manometer is one that connects both ends of the tube to a pipe that it's measuring the pressure in. And so it's called a differential manometer because with a differential manometer, instead of measuring the pressure relative to atmospheric, you're using it to measure a pressure difference within a pipe. So you'll notice that this manometer is connected to the pipe some distance apart. One of the taps is upstream, one of the taps is downstream relative to the direction of fluid flow. And this particular manometer is connected to a horizontally oriented pipe. And we like that because it makes things relatively simple for us. The way that you can use a horizontal pipe, a differential manometer is going to tell you the pressure difference by being the delta H that's measured, and then you look at the difference in the unit weights between the two fluids, between the fluid that's going through the pipe and also that same fluid is inside this differential manometer until we get to the manometer fluid. Now look at the image. Why do you suppose that the left side of the manometer fluid is lower than the right side of the manometer fluid? What does that tell us about what's going on inside of the pipe and pressure? Let me put it a different way. If the fluid wasn't flowing at all through the pipe, like if the fluid was stopped, then what would you expect to see in the differential manometer if there was no fluid flow through the pipe? It would be equal on both sides because there'd be no reason for it to have a deflection. All right, but in this case, the fluid is flowing and there is a deflection. So what does that tell us about the pressure at 1 compared to the pressure at 2? Okay, the velocity is doing something with the pressure. If we're just going to construct like greater than, less than statement, what would you say about the pressure at 1 versus the pressure at 2? The pressure at 1 is greater than the pressure at 2. And so we can observe the effect of that with this differential manometer. The fluid pressure is higher here, and it's kind of deflecting the manometer fluid by delta H because of it. Now the reason why the pressure at 1 is greater has to do with pipe friction. And later on in the semester we'll start looking at equations to predict how much pressure loss occurs when water is flowing through a pipe. And we'll do the same thing in the lab too. We'll physically measure a pressure difference that occurs due to pipe friction. But for now, just know that inside of the manometer, the hydrostatic equation applies, and we can use those static conditions in the manometer to predict a pressure difference that arises due to non-static conditions. And so, water's flowing through the pipe, but water is not flowing through the manometer tube. Inside of this secondary tube, conditions are static in here. It's in equilibrium because the pressure difference caused that deflection, delta H. So that's a horizontal pipe. Sometimes they'll be horizontal, sometimes they won't. If a pipe isn't horizontal, then this is the equation that will apply for a differential manometer. And you'll notice that there's some similarities here. Delta H is on the right side of both equations. The difference in the fluids is on both sides of these equations. But the more general equation that's always valid, whether that pipe is horizontal, inclined, or not, P sub Z stands for piezometric pressure. And piezometric pressure is something we're going to talk about. It's a way of differentiating between what component of a pressure change is due to an elevation difference and how much of a pressure change is due to pipe friction. Because in piezometric pressure, you're keeping track of not only the pressure at a location, but also its elevation above a datum. So let me explain in a little bit more detail. Here's an inclined pipe. And this inclined pipe is similar to the other one. There's a location 1 and a location 2. And I've numbered them so that location 1 is upstream and the water is flowing towards location 2. The pressure at 1 and 2 is different inside the pipe. Part of the reason why the pressure at 2 is lower than the pressure at 1, part of the reason is because of that pipe friction I was talking about earlier. And although we're not yet at the point where we're going to calculate how much pressure loss there is in a pipe, we should mentally still be able to understand and keep track of the idea that pressure decreases in the direction of flow due to pipe friction. You know, that's why the water is flowing from 1 to 2, is because water moves in the direction of decreasing energy. That's why water flows downhill, or that's why in a pipe, an enclosed pipe where there is no downhill, so to speak, the water flows from high pressure to low pressure. So in this next slide, the inclined pipe, part of the pressure difference is due to pipe friction, but also location 2 is higher in elevation than location 1. So there will be a hydrostatic component to why the pressure is lower at location 2. So there's two reasons there. Now, we can see from this differential manometer a deflection. And in this case, that deflection is only accounting for the pressure difference that's due to pipe friction. If we stopped the flow through the pipe, think about now, it shows the arrows that's indicating fluid flow, but if we closed a valve and now there's no water that's flowing through the system, then delta H inside that differential manometer, it would cease to exist. It would flatten out, and both of those liquid elevations on the left and the right of this differential manometer, it would be level. Even though it's connected to the pipe at different elevations, that deflection only exists when the water is moving, and so it's measuring and quantifying how much of the pressure difference between 1 and 2 is due to pipe friction. All right, so let me take you through the process of how we can calculate, first of all, the pressure at 2. We know the pressure at 1. Here off to the side it says that the manometer fluid is mercury, and we're given some unit weight that we should use. The pressure at 1 is known. We have the elevation difference between 1 and 2. And then the delta H measurement is provided. So we're going to use the hydrostatic equation through this tube where static conditions exist to tell us the pressure at 2. We won't apply the hydrostatic equation through the pipe section because inside the pipe water is moving and it doesn't apply. Hydrostatic equation won't get you from 1 to 2 the direct route, but we can go through here where we have static conditions. So any questions so far before I start putting the calculations for that up on the whiteboard? Okay, well, let's start where we know something. We know something at location 1. So if we're answering the question, what is P2 given P1 is 450 kilopascals, then P1 is where we know something. And we're going to go down through a fluid, so pressure is accumulating. So plus delta Y times the gamma of water. So now that tells us what would be the pressure at this location once we've gone down delta Y through the fluid. Plus delta H times gamma of water minus delta H times the gamma of mercury minus delta Y times the gamma of water minus delta Z times the gamma of water, and that equals the pressure at 2. So the pressure at 2 is going to be the pressure at 1 plus and minus all of the changes that get us from 1 to 2 through this static conditions differential manometer tube. So let's go through the pluses and minuses again. Okay, the pressure at 1 is our known. Then we go down delta Y through water, go down delta H through water. So both of those are pluses. That gets us to the interface here. The pressure here and here are the same because they're at the same elevation through the same fluid. Now we go up delta H, so minus is because we're going up through delta H of mercury. Now we need to go from this interface up to 2, and we're going to do it by going up delta Y through water and then delta Z through water. Now some of these terms are going to cancel out because we've got both a plus and a minus. So for example, here is the plus delta Y of water, here's the minus delta Y of water. So I'm going to cancel out that term and this term, and I can simplify. I can say P2 is P1 plus delta H times gamma of water minus delta H times gamma of mercury minus delta Z times gamma of water. 1, 2, 3, yep. There were three change terms in addition to the known pressure at 1. Okay, so any questions so far about this statement that we have, that the pressure at 2 is the pressure at 1 plus and minus the changes? Same thing we've been doing already today. But now we could just substitute in some numbers for that. And so pressure at 2 is going to be 450 kilopascals. Actually, let me bring it up on the screen so that it's recorded into the video. Okay. Here's our sketch, and here's how we go through and calculate the pressure at 2. So the pressure at 2 is the 450 kilopascals plus the 490 that we pick up by going downward through 5 centimeters of water. That was the deflection on the left side of the manometer tube, the delta H of water, minus the delta H of mercury. So then we're subtracting 6650 pascals. And then finally we're going up 1 meter of net elevation between 1 and 2. And that's because the pipe itself was inclined. And so that remaining 1 meter was how much the pressure changes just by virtue of the fact that the right side of the pipe is higher because it's inclined. So the pressure at 2 is going to be 434,000 pascals. So it's lower for 2 reasons. It's lower because of the elevation difference, and it's lower because of pipe friction, so energy losses. But how much is from one versus from the other? That's what piezometric pressure will allow us to predict. Before I move on to the second part of the example, any questions about this first part? It's a learned skill to create a statement like this. It seems pretty abstract at first, but if you just kind of keep focused on the sketch and how you're getting from 1 to 2, and the dimensions are a little bit strange, that there's a separate delta y and a separate delta h and so on, but if you're just applying the down means pressure is accumulating positively, up means pressure is decreasing, then you'll ultimately be okay. The second part of this example says, what is the change in piezometric pressure? What is the change in piezometric pressure? And so the delta P sub z is delta H times the difference in the unit weights between the two fluids. So gamma of mercury minus gamma of water. So we know the net pressure difference between the two, but this is asking the piezometric pressure is how much of it's due to pipe friction. And so 0.05 meters is the delta H, and then the difference in the unit weights, 133,000 newtons per meter cubed minus 9810 newtons per meter cubed. So the delta P sub z is 6159.5 pascals. So you can think of that as the amount of the pressure change that's due to pipe friction. So the total pressure difference between the two is about 16 kilopascals, from 50 kPa to 34. 6 of that is due to pipe friction. The rest is due to the 1 meter elevation difference between the two locations. Any questions? Differential manometer, inclined pipe? No. Now remember that sometimes we use pressure to measure differences in potential energy between two locations. We can also express that in terms of piezometric head rather than piezometric pressure. And so piezometric pressure is at a certain location, it's pressure plus gamma times z, where z is the elevation above some datum that we would measure all elevations in the system. By contrast, the piezometric head, each of these terms has been divided by gamma. So it would be the pressure head and the elevation above some datum to get the piezometric head rather than the piezometric pressure. So if you want to find the change in piezometric pressure, that's the approach that we just looked at the second part of the example. But you could also identify the change in piezometric head by simply having the delta H times the ratio of the unit weights minus 1. Okay. Now we're going to move on from talking about manometers and discuss how the atmospheric conditions vary as a function of elevation through the atmosphere. And so maybe you've seen photos like this before of weather balloons. And you'll notice that there's quite a lot of slack here on the runway where they haven't filled the weather balloon all the way. And the reason why is that as it goes up through the atmosphere, the gas that's inside that weather balloon is going to continue to expand. Maybe you've known, like if you release just a helium balloon, it goes up through the atmosphere, but then it'll often burst because it continues to expand until the elastic doesn't have the strength to contain all of the gas any longer. Now the reason for that is that as we go up through the atmosphere, both the temperature and the pressure is decreasing. And that decreasing temperature and pressure, they're related. The temperature is decreasing because the pressure is decreasing. Now, the atmosphere, our atmosphere right here at ground level is about 80% nitrogen, 19% oxygen, 1% everything else like carbon dioxide, noble gases, helium, hydrogen, and so on. So as we go up, it's a fluid in the atmosphere. And we could look up a unit weight for air, just like water has a unit weight. And you could apply the hydrostatic equation through a gas in the same way that you could apply it through a liquid. This temperature component, though, the change in temperature, is that if you want to find the temperature at some elevation, then you'd have to know the temperature at the ground or sea level at some location where it's known. And then this alpha parameter here, the lapse rate, tells you the relationship between what the temperature is changing with each unit of elevation difference here. So what this diagram is showing is that the temperature lapse rate is about 5.87 Kelvin per kilometer of elevation that's gained through the troposphere. Now you can substitute that temperature lapse rate equation into a different formula that will predict what's the pressure at a certain location in the troposphere if you know the pressure at the other altitude. And so at like the sea level or at some location where you know the pressure, you can find the pressure at another location by applying this equation. And so it's simultaneously taking into account what the temperature would be at that elevated location and how much the gases expand, and therefore the pressure decreases as you go up through the atmosphere. Okay, so just to get a feel for how this equation looks, let's consider the case of the Burj Khalifa. This is a building where you'll actually notice the pressure difference as you ride the elevator up to the observation tower. And the observation tower is only about 2/3 of the way up, and still your ears are popping like crazy. So let's say that at the bottom of the Burj Khalifa, which is about 10 meters above sea level, let's say, for instance, that the temperature there is 30 degrees Celsius, and the measured atmospheric pressure is 97,189 pascals. So if we have that known elevation and known temperature and known pressure here at the base, then at the top, which is 828 meters tall, what's the air temperature? And so to calculate the air temperature, you're just using this component of it, the temperature at some known elevation. So let's predict the air temperature aloft, and then also what would be the air pressure aloft. And you'll notice here that there's a couple of constants that are given. First of all, the lapse rate. Previously we saw it in Kelvin per kilometer. You can also express that in terms of how much the temperature is changing with each additional meter of elevation. And then the R value, the gas law constant for air in terms of joules, kilogram, Kelvin, that you'll need it to be in if you're inputting the temperatures in Kelvin and all the other standard units in the SI system. So, all right, I'm going to pause the recording, give you some time to calculate these two things, the air temperature at the top and also the pressure aloft. All right, let's go through the solution. I've just realized I have a mistake in my solution, a small mistake. Let's go through and I'll show you where it is. Okay, first of all, we need to calculate the temperature in terms of Kelvin. Now, at the top, it's going to be the starting temperature of 303.15 Kelvin and then minus a change. You'll notice that I have the delta Z. I put 0.828. That's wrong. It should be 0.818. So your answer may be slightly different than mine. I have 298.27 Kelvin. What is it for those of you who use the correct delta Z? 298.35. 0.35. Okay, so a very small difference in temperature, but I am going to update my notes with that change. But the method is that the temperature is going to be noticeably cooler up there, and it is. It's noticeably cooler up there. Now, the air pressure, the reason why your ears pop on the way is here in the numerator, inside the brackets, it will be the temperature aloft. The denominator would be the temperature down below, and then this exponent factor that we're using, G divided by alpha times R, it's unitless. That's a unitless term once we combine everything that goes into it. So 5.823. That tells us that the pressure aloft is going to be about 88.4 kilopascals. Maybe slightly different once I update that temperature. But goes from 97 kilopascals to about 88 kilopascals. So that's the atmospheric pressure variation. All right, so we are out of time for today. I will grade those quizzes, put the scores online, and bring your paper back. Look for the homework assignment. It'll be posted later today. And I'll see you on Tuesday.